This is a video about a cosmological thought experiment and its imagined consequences. A thought experiment is a hypothesis that lays out some conditions and suppositions and tries to think out what the results would be if those suppositions were accepted as accurate. To be useful, it should describe reality, make predictions, and be simple. The thought experiment in this case involves dark matter and dark energy, in particular the observable effects of expansion, also known as negative pressure. So what is this idea? It started with wondering about universal expansion by way of a cosmological constant, commonly referred to as lambda. The same lambda as in lambda cold dark matter models, or similarly expansion by means of dark energy. Current thought is that we don't see the effects of it locally because it is universal and featureless, and so very tiny and incremental. Any effects are overridden locally by gravitation and atomic forces. This current supposition leads to a conundrum: the tethered galaxy problem. The universe is observed to be expanding, but galaxies are gravitationally bound, supposedly overriding this expansion. So at what point and under what conditions would this expansion exceed the gravitational influence of galaxy to galaxy and start separating galaxies due to expansion? That got me wondering, why have we not observed any effects of expansion locally? It's postulated to be featureless and uniform. So even with gravity overriding this expansion, is there any way to detect its effects locally? Not if it is featureless and uniform. Its effects are observed in redshift, but don't appear to be detectable on a local laboratory level. Here is where the thought experiment begins. So what if negative pressure wasn't uniform, even by a little bit? What would that look like? Negative pressure would exert an apparent force, as it is a bending of space-time, so it would appear as a force opposite gravity. Or would it? When we think of speed, what matters is a vector. We don't reverse speed, we change its vector. This is how we detect acceleration. Deceleration is a descriptor of acceleration in a vector opposite current motion, and isn't really a thing in physics. So, thinking about space-time geometry, what you're measuring is curvature, the angle of a particular mode of space-time in 4 dimensions, the tensor. And as far as the path of objects, all that an object responds to is that angle, that slope, not whether or not it is positive or negative curvature. It's a vector. So imbalanced negative pressure would show up as a kind of invisible mass, opposite of where the expansion was occurring. This immediately brought to mind dark matter. If dark matter was a manifestation of negative pressure instead of a mass, what would be different? For one, it would never be detectable as a particle, never give off light or decay, never be measurable as motes or small objects by imparting extremely local curvature like a primordial black hole. It also would never cluster, never aggregate into point masses, never exhibit behavior of normal matter, never heat or cause heating through momentum transfer. So why would it appear to gather around matter? What is its source? What are its limits that cause this imbalance? To continue this thought experiment, we would have to suspend some ideas we currently hold, just to see where the consequences lead. First, we do not consider a cosmological constant. Uniform featureless expansion is, for now, excluded. Second, concepts of dark matter as a particle or mass. Third, dark energy also as uniform and featureless. This leaves us with a lot of unaccounted for elements and massive imbalances, but we'll come back to that. For now, we have a negative pressure that looks like gravity, extra gravity, surrounding masses. Why would it look like it surrounds a galaxy? Why is it shaped like that? What causes this diffuse gravitation to vary at all? Is it the size of the galaxy? Here's where I will mention modified Newtonian dynamics, or MOND. Mond postulates low accelerations and galactic radii as the varying factor. This works for a lot of spiral galaxies. For this idea, it is not sufficient. We are looking for something that explains elliptical galaxies as well, and cluster behavior, because we are looking at an explanation for all dark matter and its effects, as well as Lambda, the cosmological constant. So the size of the galaxy, its mass and radius, can't be the sole varying factor. What then? What varies around galaxies and clusters? Voids. Areas of extremely low density. The definition we'll use for a void is a density of less than 0.1 atom per cubic centimeter, or roughly less than 100,000 atoms per cubic meter. If we, for now, try the idea that the magnitude of the dark matter effect, this negatively curved space, this negative pressure, is tied to the amount of void and how sparse any matter is, that does give us some of this imbalance, but it does not rely solely on galactic radius and mass. So if it varies, it would vary based on void scale? What happens if we add that to the imbalance? And how is that any different from the tethered galaxy problem all over again? Let's define the void's behavior, hypothetically. We take this void. We give it room. How much negative pressure does it exert? If we postulate that it is related to the scale of the void, we can give it more and more room, and it expands faster and faster, exerting more negative pressure at its boundaries. As void scale grows over time, expansion accelerates. This sounds like accelerating dark energy. The larger the region of void, the more effect it has on boundary masses. Similarly, the smaller the region of void, the less effect on boundary masses. Which sounds like the behavior of dark matter, which doesn't aggregate, and appears to get more sparse as you get to the interior of spaces like galaxies, with relatively small voids with more matter present. This behavior, this negative pressure exerting negative curvature, would be opposed by standard matter both by virtue of attenuation in the presence of matter, and by positive curvature due to standard matter gravitation. So we'd expect smaller galaxies in areas not influenced by other galaxies to have more dark matter effect, and galaxies of larger sizes, or in more crowded regions of space, to have less dark matter effect. Does this violate isotropic expansion? Is it postulating anisotropic expansion? Matter is isotropic in distribution, that is, anywhere in the universe you go, you see a lot of the same, galaxies, clustered, and in isolation. So matter is not homogeneous until you get to larger scales, but it is isotropic. Expansion could similarly be so, isotropic, but not homogeneous. In the classic example of a raisin loaf to explain expansion, we'd be taking the analogy further, maybe too far, to point out that expansion in a raisin loaf is isotropic, but not uniform. A loaf expands in total due to the expansion of many individual bubbles of gas, but a loaf ends up one expanded shape. What effect would this have on the calculation of the Hubble constant, the rate of expansion over time? What this might mean for the Hubble constant is that it is an average of all of this expansion instead of an absolute measure, and would be more uniform the further out you looked. Locally, it would be very difficult to recover the Hubble constant as the variation in expansion is not smoothed out in the nearby universe. It would also postulate that light that passes through mostly regions of matter, instead of regions of void, would expand less, and would have to be adjusted in calculations of expansion, especially close by. For longer distances, the amount of matter versus void that light passes through would average out, that is, how much of it is stretched by expansion. So already we have some predictions or consequences. Galaxies that appear more elliptical should be interior to a cluster, while spiral galaxies should be in the outskirts. The Hubble constant should not be recoverable locally. Dark matter should give off no particles or have any influence in areas of high density. dark matter should have no substructure that is denser than any outer profile. The idea suggests that galaxy morphology should be more due to position within and around other galaxies and voids than by age or evolution. But wouldn't this mean galaxies could be imbalanced in their dark matter profile? The presence of voids shouldn't be absolutely equal everywhere. They should be lopsided, warped, or distorted when the effect be masked more to one side than the other, when they're adjacent to a cluster, for example. This would be another prediction. And it bears out when we look at observational data. Spiral galaxies adjacent to large clusters appear lopsided, uneven, which would follow from an uneven dark matter effect. What about galaxies entering the interior of a cluster? Shouldn't they lose their dark matter profile? We look at the observational data. We do see this with galaxies of varying sizes. It's identified as ram pressure stripping, but under the idea we're discussing, it should instead spin out as the dark matter effect is attenuated. And there should be a lot less heating, as the matter is not tidally stripped or colliding with the intracluster medium. What about galaxies that exit the interior environment of a cluster? Shouldn't they start gaining a spiral profile? Again, observational data. Ring galaxies that appear to be ellipticals with an outer ring of gas and dust appear outside of clusters rather than interior to them, where the dark matter effect could again manifest and help them retain newly ejected gas and dust instead. One side effect of this model is the possibility of galaxies appearing to have no dark matter at all. At the time the idea was initially drafted in 2010, this was included, but was culled out due to no then current observational data of galaxies appearing to have no dark matter. This has changed recently, as some galaxies have been documented that appeared to lack dark matter. So one could suggest the model made a prediction that bore out later, that wasn't then in observational data, in two ways. Some galaxies will appear to have no dark matter for two reasons. One, from being in a more crowded region of other masses, masking out the dark matter effect. Two, from galaxies that have recently exited such an environment, as they will have lost any high-velocity gas and dust, which is one of the primary ways in which dark matter is detected. Now we can start to readdress the elements that we previously removed. First, the cosmological constant. Is a cosmological constant necessary if the mass of dark matter is instead an effect, and the collapse of the universe is less likely? Would this piecemeal expansion be enough to make up for the missing cosmological constant? What difference is there in this model from other Lambda cold dark matter models? And what about halting expansion and early structure, both of which rely on dark matter to some extent in current models? For this we return to part of the idea that relies on the scale of the void. In the earliest universe, the scale of voids would have been small, but still would have driven large-scale structure in addition to gravity. It would serve to clear out voids of matter, as the negative pressure of expansion would have reinforced the aggregation of matter. If two voids are in opposition, larger voids will overtake smaller voids. Voids will clear themselves of matter. This differs from some Lambda cold dark matter models, which predict a large number of cold dwarf galaxies in these voids. Regarding halting expansion, we return to a growing void. At large enough scales, this expansion, though piecemeal, could exceed the recombination of virtual particle pairs and cause matter and energy to precipitate. This would drastically reduce the void scale and introduce matter and gravitation, which would drastically reduce the rate of expansion, if not stop it. This could also answer the conundrum of the theoretical expansion rate of a vacuum and the observed rate. If it is constrained by this limit of scale in terms of magnitude and causes matter and energy to manifest if it exceeds the speed of recombination of virtual particle pairs, it would never reach the theoretical limit of 10 to the power of 120, but instead manifest at the scale of the region of vacuum and self-limit by the recombination speed of virtual particle pairs. This resembles reheating in inflationary cosmology. So with this idea, we have a potential unifying explanation for the cosmological constant, or lambda, dark energy, dark matter, galactic evolution and morphology distribution, the tethered galaxy problem, the Hubble tension, fine-tuning, large-scale structure, inflation and the end of inflation, and the vacuum energy catastrophe. It has the potential to describe a lot of reality. And for predictions, it should be possible to calculate the expansion locally, to create a hard vacuum and attempt to measure expansion or negative curvature, to calculate from adjacent voids the local dark matter effect and measurable rates of expansion from supernova, to create a more accurate map and prediction of the gravitational lensing results of dark matter effects, to calculate the void scale needed for the origin of the universe, and to calculate the amount of time that must pass until the void reaches this scale again. Left unknown is the potential to detect anything from a previous expansion, or if this could result in any new technologies or analysis or instruments. In the initial paper, it was brought up that there should be a distortion in the dark matter effect around the Milky Way in the direction of Andromeda. This appears to have been realized. Galaxies without dark matter were postulated as being possible. This also appears to have been validated. It has the potential for prediction. Lastly, if it unifies a lot of varying descriptions and removes fine-tuning as a concern, it is potentially a simpler explanation. No extra dimensions, no multiple universes, no special conditions of the vacuum, no inflatons are required. This isn't due to a distaste for these explanations or any prejudice. It is that a possibly simpler explanation that makes predictions has the potential to be a more useful description. One thing this does bring up: if the beginning of the universe resembles precipitation from an expanding void in this model, it could mean that the universe began from a similar state to what we postulate as our future. It potentially eliminates the Big Bang singularity, instead opting for a universe from a literal nothing, a vacuum. This could be one in a series of those precipitations. We would have a hard time detecting if this was the first from a nascent vacuum, or just one in a potentially infinite series, but it might be possible. I didn't set out to come to this conclusion, that the Big Bang might not represent the beginning of the universe. And this was a concern when finalizing this idea. It might be seen as an attempt to reintroduce steady state, or an attempt at tired light. Neither was on my mind when coming up with this, and neither truly is compatible with this idea. The end of inflation stays the same in this model, but it does mean that causally we may be in an infinite universe in space and time, extending an unknown distance into the past. The initial paper with references and citations and a first attempt at a mathematical characterization of this idea is in the description. The first version was from 2010 and was given minor revisions for publication in 2020. Thank you for your time.